Okay, so this lecture is on one of the most potentially consequential impacts from climate change, and that's human deaths, both from hot and cold temperatures, under the kind of present climate, and then what the implications would be under climate change. So, class learning outcomes for this module can be kind of divided into five sections. So, there's a background kind of motivation section for learning about these things. And then the other four have to do with kind of in the present time period or how things have changed in time, either historically or into the future. So basically how many deaths there are from cold versus heat, variation in the vulnerability to deaths from non-optimal temperatures in the current climate, and how those have changed historically over time, and then how those are projected to change in the future. Okay, so first, this motivation. So a main motivation is just that ambient air temperatures actually tend to be associated with a lot of deaths. So they can be considered to be a factor statistically in 1 to 10% of all human deaths, which is a huge number. And in fact, these are considered to be the largest climate impact in monetary terms, in terms of the climate's damage function or the social cost of carbon. So that's exemplified by a couple of studies here, one globally and one in the United States. So this one is breaking down the total social cost of carbon into four sectors. So the total social cost of carbon they have here as $185 per ton of CO2. So that's the total economic damage that releasing a ton of CO2 does to the economy, according to these calculations. Their sectors, they have mortality as the largest sector, so much larger than sea level rise or the energy sector, and then agriculture is a close second. And then also in this one, that's just for the United States, economic damages from climate change in the United States. This is expressed a little bit differently. This is temperature change and then direct damage as a percent of GDP over here. But you can see that mortality and VSL, value of a statistical life, is the section that is by far the largest here of their sectors. So they use some different sectors. They have 9 instead of 4, but all of these other ones are much smaller than the mortality one. So obviously, death is a very serious thing, but it's also the largest monetary component of these calculations that go into, cost-benefit analysis of climate change policies. Okay, but speaking of climate change policies, climate policies, which are basically energy policies, will affect hot and cold deaths in more ways than just their effect on greenhouse gas emissions and thus temperature. So there's a couple of more ways to think about this. One is just the economic development lens, that looking at pictures of a low energy consumption society versus a high energy consumption, high income society. This is Singapore and this is a slum in India. We can tell that high energy consumption societies are going to be much more resilient to extreme temperatures, just from looking at pictures. And so any energy policy that makes it more difficult to scale up energy could potentially cause more deaths from non-optimal temperatures. And even within high energy consumption societies like the United States, energy insecurity or not being able to afford energy is a very big deal. So this is a study from the Center on Global Energy Policy at Columbia University, where they found, this is for the year 2020, that 12.2 million households left their homes at unhealthy temperatures to avert high energy bills. And 5 million were unable to use heating equipment, and 6 million were unable to use air conditioning, essentially because energy prices were unaffordable. So price makes a big difference here. And here's another example, kind of in the same vein. This is a story from The Economist, in the context of a couple of years ago when COVID was still a big killer. The headline, "Expensive energy may have killed more Europeans than COVID-19 last winter." So this is in the context of the Russian-Ukraine war that was causing energy prices to be much higher than they would have been otherwise. And what they're showing is death rates here as a function of time of the year, where deaths basically go up in the winter when it's cold and then come back down in the summer. And they're saying because of high energy prices, the deaths are going to be much higher, according to their modeling, than average. And then there's a big difference between whether or not it's very cold or more mild. So colder temperatures are going to be causing an even further increase in death than a more mild winter. But either way, it's elevated because of high energy prices. So we think about climate policy and energy policy just affecting that temperature component via its impact on greenhouse gas emissions. But we really should also be thinking about the effect on energy availability and energy prices as well. Okay, so that's a little preamble for thinking about policy, but let's get into more of the details on deaths from hot and cold temperatures. So first, a little bit on the physiology of this. Is the case that people do die of hypothermia in the cold and of heat stroke and dehydration and electrolyte imbalances in very hot temperatures. But those are pretty rare. So in both of these cases, these are direct temperature leading to human deaths. But in most of what we're going to be talking about here, it's really just the temperature facilitated a death that was predominantly caused by another cause or a comorbidity. So these tend to be either cardiovascular or respiratory problems. So I have cardiovascular and respiratory issues on both the hot and cold side here. And in both cases, cardiovascular tends to be, heart attack, stroke, and respiratory problems like asthma, bronchitis, or respiratory infections. And the mechanisms are a little bit different. So on the cold side, when it's cold, the body constricts blood vessels to conserve heat. And that means that you're basically going to increase blood pressure, which has deleterious effects. On the heat side, the heart must work harder to help cool the body down. And then on the respiratory side of things, main causal pathways are increased inflammation and sensitivity of the airwaves under cold and irritation due to increased ozone production from higher temperatures in hot conditions. There's additional causal pathways on both the hot and cold side. So on the hot side, foodborne and waterborne illnesses, tend to be more prevalent when it's hot. Increased growth of bacteria in food and water sources. You see different rates of injuries from outdoor activities and drowning. You actually see relationships with crime and temperature. On the cold side, there are immune system issues. So cold, dry air basically can damage our mucosal barrier, which is a first-line defense against respiratory infections. And when it's colder, it tends to be drier, and that makes, when you sneeze, your germs are in an aerosol, and the dryness means that the aerosol evaporates the water quicker, and so then that aerosol can move further. So that's one of the mechanisms by which we think, cold and flu season is a season that's during the cold time of the year. There are also different activities associated with cold, like potentially increased car accidents, things like that. So the bottom line here is that hot and cold temperatures are associated with health problems and with deaths, but most of them have a primary cause that's not hypothermia or heat stroke. It tends to usually be cardiovascular or respiratory problems that then are exacerbated by extreme hot or cold temperatures. Okay, so how is this measured? So this is measured in what tends to be called in these scientific papers exposure response functions. But in the literature review write-up I did, I call them temperature death risk relationship because I think that that's more descriptive. And so this is basically what that looks like. So you have temperature here. You're kind of like looking over some window of time. This would be days. And you're looking at the risk of death, the relative risk of death. And so this three-dimensional surface can be collapsed into two dimensions over here. And this is the type of representation of this that will be focused on the rest of this lecture. So you really need to understand this. So what we have here on the bottom is daily temperature, daily mean temperature. And this is a histogram for London over the period 1993 to 2006. So you can see that there's kind of, this is very common to have kind of a bimodal distribution in temperature, where you have a kind of a peak in the winter and a peak in frequency in the summer. But this is showing, yeah, that we have, you know, a common temperature around 10 degrees in the winter in London and something like 16 degrees in the summer in London. And so that's your baseline daily temperature. And up here you have the temperature death risk relationship that's derived from statistical relationships between daily temperatures and daily death rates. And this is expressed as a relative risk relative to a minimum daily death rate. So what this means, 1.5 would mean that you are 50% more likely to see a death with that temperature than you are on a day that minimizes that temperature death risk relationship. And this lag component over here means that you could be accounting for persistence of having many days in a row at the same temperature. So again, these are all statistical relationships just relating deviations in death rates at various locations to daily average temperatures. And these studies are not, you know, looking at death certificates and saying like how many people does it say died of hypothermia or heat stroke. Okay, so that was for one location. That was for London over a particular time period. And this is the same graph, but for 13 different locations. And so we're trying to pay attention to this temperature death risk relationship here. And we see that they tend to be either U-shaped or J-shaped with a steeper slope on the warm side. So Tokyo, Japan has kind of a J-shaped one. It looks like Madrid, Spain has more of a U-shaped function. New York is very J-shaped here. So that's telling us that death rates really spike for extreme heat. And something interesting here is that what you'll notice is that most of the time is spent in colder than optimal temperatures as opposed to warmer than optimal temperatures. And so we can see that here in New York, that here's the optimal temperature, the minimum mortality temperature is called. So all of the risk ratios expressed relative to that. If you look at the histogram of daily temperatures, that's much larger here on the left side than on the right side. So you have more days on the cold side of this optimum than on the warm side of this optimum. And one way of expressing that is to say what percentile of the daily temperature is this minimum mortality temperature or optimum temperature at. And that's what this graph shows here for 43 countries, and there's many cities within each country. But if you look on the left versus the right side of the 50th percentile, so dots on the right side are countries with a minimum mortality temperature that's above the 50th percentile of the daily temperature distribution. And dots on the left side are countries with a minimum mortality temperature that's colder than the 50th percentile of the daily temperature distribution. And what you'll see here is that 39 out of 43 countries had mean optimum temperature percentiles above 50%. So what that means is that in those 39 out of 43 countries, they spend more time in colder than optimum temperatures as opposed to warmer than optimum temperatures. And so that has consequences then for the number of cold versus hot deaths. So in the current climate, deaths associated with cold outnumber deaths associated with heat by factors of 5 to 10 globally. So in this study, Gasparini 2015b, they found that the global ratio of cold deaths to heat deaths was 9.4, meaning that you have 9.4 times more cold deaths than heat deaths. And this is shown here broken down into these 4 categories of temperature for 13 countries. And what we see is all of these have this large spike for moderate cold. So moderate cold tends to be the temperature category that's associated with the most deaths. And the way they define these categories is the 0 to 2.5th percentile of daily temperature is the extreme cold. The 2.5th to 50th percentile temperature is the moderate cold. The 50th to 97.5 percentile temperature is the moderate heat category, and above the 97.5 percentile temperature is the extreme heat category. And so for all of these countries, it's that moderate cold, that 2.5th percentile to the 50th percentile, part of the temperature distribution that's causing the most deaths. And that's even in hot countries like Thailand and Brazil. It's still that moderate cold part of the distribution that's the most deadly. And so that's not because moderate cold is actually less deadly than extreme cold, or moderate cold is less deadly than extreme heat on a per exposure basis. It's that we actually just spend a lot more time in the moderate cold part of the distribution as opposed to the other parts of the distribution. And so we'll see that in later graphs. But I think one point of emphasis here is that even in hot countries, it's cold deaths that outnumber heat deaths. So even in, say, sub-Saharan Africa, this ratio is 58.3 to 1 cold deaths to heat deaths. So everywhere, cold deaths outnumber heat deaths, according to this study. Okay, so thinking more about this kind of variation in the current climate, variation in vulnerability to cold and heat, it's pretty interesting to compare these functions for different cities. So here's a kind of characteristic example showing acclimation to the local climatological temperature distribution. So on the top we have Winnipeg, Canada, the temperature distribution, daily temperature distribution, and the temperature death risk relationship. And then of course this is expressed the same way, the risk of death relative to the temperature that minimizes the local risk of death. So here this goes up to plus 100%. That doesn't mean like 100% of people die or something. It just means that your risk of death would double if the function was actually up here. So anyway, we see, okay, a daily mean temperature, like let's look over here, a daily mean temperature of 27 degrees Celsius or 84 degrees Fahrenheit. Remember, this is the daily mean, not the high that we're used to thinking about, but the high and low averaged together. So that's a very hot mean temperature. A daily mean of 29 Celsius or 84 Fahrenheit in Winnipeg, Canada is associated with a substantially elevated death rate. And you look here, it's actually even more elevated than a death rate at negative 30 degrees. So like if I were to draw a line here, that it's above even negative 30 degrees. So this is an extreme temperature for a cold city. But what if we compare that to Tucson, Arizona, a hot city? Well, it turns out that this temperature, this same temperature, is actually the optimum temperature for Tucson, Arizona. So that's the temperature that actually minimizes the death rate there. So that's showing that we have strong kind of acclimation to the current climate when we look across space today. And we can see that more systematically in this study that looks at the minimum mortality temperature. So that's this temperature here for different cities. And it's just amazing to appreciate the range of this minimum mortality temperature. So it ranges on the cold side for a country average of 14 degrees Celsius or 57 degrees Fahrenheit for Estonia here to 31 degrees Celsius or 88 degrees Fahrenheit for Kuwait. So that's a 17 degree difference in country average. And these bars here are the cities within the country. So if you're going to go to actual cities, it'd be even that much larger of a range. But 17 degrees is a huge range, even at the country level. And so what is responsible for this range? Well, you might think, okay, Estonia is colder than Kuwait, and that's essentially what's going on. So this is kind of an amazing graph here. That what over here they're plotting the temperature that minimizes the mortality rate, that minimum mortality temperature, so the same range I was just talking about. And they're plotting it against the country's most frequently experienced temperature. So that's the mode of the daily temperature distribution, not the mean. It would be, when you look at these plots like this, this is the mode. This is the most frequently experienced temperature. This is the most frequently experienced temperature, where the mean would be like, somewhere over here. So the country's most frequently experienced temperature is highly predictive of the country's minimum mortality temperature. And so one way of saying that is that warmer climates are strongly associated with reduced sensitivities to hot temperatures. The flip side of that coin would be colder climates are strongly associated with reduced sensitivity to cold temperatures. But regardless, this is an amazingly tight relationship showing really a lot of acclimation to local climate. And so this literature is not quite sure, it seems like, why exactly this is, why we seem to be so adaptable to the local climate. Certainly, heating and cooling technologies play a role, and they have larger adoption in locations that routinely experience cold and hot temperatures, respectively. There certainly seems to be just behavioral and informational differences in different communities based on experienced temperature and kind of knowing what to do when extreme temperatures occur that are relatively common. General economic development certainly plays a role, and so the basic example of that is just air conditioning in hotter climates. But that certainly can't explain all of this tight relationship, because in a lot of hot countries, these are low income countries, and so they have very low adoption of air conditioning. So that's what this plot is showing here. We have income within country on the x-axis here, and then we have share of households on the y-axis here that, for example, have air conditioning. So this is showing that as you get richer, you're more likely to have air conditioning. But once you make $100,000 a year in Brazil, then you're at a rate of about 30% of households have air conditioning. But what's also shown is the actual income distribution. And so you see that's centered somewhere between $1,000 and $10,000 a year. So that's going to be something like 5-10%, say, air conditioning. And you see similar thing in India. I believe India, there's only about 5% have air conditioning. But even these hot, low-income countries, it would certainly benefit them to have a larger adoption of air conditioning. But even without it, they still seem to be relatively acclimated to the temperatures that they experience. So this acclimation means that when we look at global maps of average annual number of excess deaths due to non-optimal temperatures, so here's a map of that. And then here's it broken down into cold and hot, where, remember, cold is much more common than hot. So this color scale is much larger, spans a much larger range than this color scale. But when we look at maps of these, it's not the case that you just see, cold-related deaths are much higher in the cold regions, like you have some big area up here, and then heat-related deaths are much higher in the tropical regions. No, it doesn't really look like that at all. So just an example of that, we see more cold-related deaths in Nigeria than on the East Coast of the United States. And we see more heat-related deaths in Europe than in Indonesia. And this is not per capita, this is just the annual number. So a lot of what you're seeing here is just, kind of looks like a population density map. But still, it's interesting to compare this cold versus heat-related deaths across space. Just again, the point being that it's not so much about what the local climatological temperature is, whether or not you're more or less sensitive to hot or cold temperatures. Okay, so that's, the variation in the vulnerability to hot and cold is very relative to the location. So cold means something different in different locations, and hot means something different in different locations. Okay, so now let's move on from the present and start looking at changes with time. So looking at changes in the historical record. So this is a graphic that can help us think about this. This is actually a projection into the future, but it still can help us think about how hot and cold deaths might change over time. So on the top here, we have our relative risk of death. So this is our minimum mortality temperature here. Here's our temperature death risk relationship. So this is saying that you're, twice as likely to see a death on a day at around 30 degrees than you are at a day at around 18 degrees. And then here is a temperature distribution over a time period. So this is over the 2010s. This gray is your temperature distribution. And you can see, like we've been talking about, the temperature distribution is mostly on the cold side of the minimum mortality temperature here. So you're going to expect to see a lot more cold deaths than heat deaths. And that's what this is showing here. So this is the excess mortality. You have a lot more cold deaths over here, and then heat deaths are down here. And what we're showing here is a warming situation. So this is under this RCP 8.5 emission scenario from this climate model and the period 2090 to 2099. That's what this green distribution is. So the whole distribution just shifts to the right a little bit. And that has implications then for death. So you see that the cold deaths decline. So this green excess mortality is now smaller than the gray one over here. And the heat deaths increase, and they increase actually by a lot here. And that's because of the shape of this function, that this is relatively flat on the cold side, but then steep on the warm side. So putting this distribution more into this steep area causes a large increase in excess heat deaths. So what that means is that even if cold kills more than heat does, warming can still increase deaths if heat-related deaths increase more than cold-related deaths decrease. And that is what you're seeing here. It's kind of hard to tell, but you see a decrease in cold deaths and an increase in warm deaths. In the warmed climate, this green part, the cold death part, is still larger than the warm death part. But warming caused an increase overall in deaths because warm deaths increased more than cold deaths decreased. Okay, so that's this very simple exercise of taking this temperature death risk relationship and just shifting the distribution under it. But of course, in reality, changes in deaths will depend on other things, like how exactly like the shape of the distribution, the temperature distribution shifts, and then how this temperature death risk relationship might change over time, because we see that it has a very different shape in different locations. So there's no reason to believe that it should stay steady at any given location. And so the optimum temperature might shift, the shape of the function might change. And also, remember, this is all relative to the temperature that minimizes the death rate. But that background death rate is certainly going to change as well. So you could have a situation in, say, 2070 where all deaths are decreased by 50% or something like that. And that wouldn't necessarily show up in this because it's all normalized relative to the temperature that minimizes the death rate. But regardless of that, the change in shape is interesting to think about. So a flattening of this shape would indicate an increase in resilience to non-optimal temperature. And particularly if it's flattening on the right side, it would mean that even in isolation, deaths associated with heat can decrease over time despite warming. So isolating the heat component instead of just thinking about the net change in deaths. So we see some evidence from that in this study here. This is the function in 1993 in black, and then the function in 2006 in blue. And in these 7 countries, 1, 2, 3, 4 show a flattening on the heat side of things. Looks like 2 show pretty much no change. And then Australia is the outlier, showing apparently an increase in sensitivity to heat. Here's another study that looked just at the United States. And this is expressed a slightly different way, but this is looking at different regions in the United States. And then here's the national. And this is just looking at the heat side of things. And from 1975 to 2018, they show a marked decline in heat deaths, just heat deaths over time. And here's another study for the United States, Bob et al. 2014, looking at all heat deaths expressed as a rate per 1,000, and then broken down into age cohort. So it looks like the largest declines were in the older age groups, the orange and the green here as opposed to the blue. Also broken down by cardiovascular versus respiratory issues, kind of showing similar declines, and then broken down by region as well. And here's another study in Japan, kind of doing similar things. Here's a similar breakdown, cardiovascular versus respiratory from the 70s to the early 21st century, and then also broken down by age group, showing the largest declines in the oldest age group. And here's one more across countries. Again, all these are just for heat deaths alone, not net deaths. This is essentially showing a decline in heat deaths in, say, 8 out of 11 countries here, where the exceptions are Australia and Brazil, showing an increase, slight increase in Brazil, but like marked increase in Australia. And this study is saying this is not due to just warming. This is due to increased sensitivity over time to the same temperature. And so it's kind of a mystery why that would occur. Some possibilities would be demographic shifts. So as populations become proportionally older, then sensitivity to heat could increase. So things like that might be confounding variables in this data as well. Okay, but more often than not, we do see kind of a flattening of these temperature death risk relationships. And here's another example for countries. So in this case, Canada isn't seeing much of a difference, but significant flattening in Japan, Spain, and the United States between the years 1993 and 2007. And so one difference here is the adoption of air conditioning. So in Japan in 1975, only 16% of people had air conditioning, and that was up to 89% by 2007. And so that you think would help explain a lot of this flattening. Similarly, in the United States in 1975, 49% of people had air conditioning, and by 2004, it was 83%. And so you'd expect to see a flattening due to that. And so that seems to be a significant part of the story. And so, again, this is just looking at heat deaths alone. This is how the IPCC describes this phenomena of increasing resilience to heat deaths. So heat attributable mortality fractions have declined over time in most countries owing to general improvements in healthcare systems, increasing prevalence of residential air conditioning, and behavioral changes. These factors, which determine the susceptibility of the population to heat, have predominated over the influence of temperature change. So societal changes like healthcare systems, air conditioning, and behavioral changes are moving faster to reduce our sensitivity to heat than the climate is changing. So that's really good news. And the news tends to get even better when we talk about net deaths or incorporate cold deaths. So cold deaths have also, just like heat deaths, been found to be decreasing, and that would also be due to increased resilience to cold temperatures. But in this case, cold deaths would also be helped out by the background temperature getting warmer, right? It's warming, and so that's also decreasing cold deaths. So when you look at total deaths or net deaths from non-optimal temperatures, they have also been found to be, decreasing in most locations. So this is from this study Zhao et al. 2021 that broke this down by location. We have 5 4-year chunks in this time series. So 2000 to 2003, 2004 to 2007, 2008 to 2011, 2012 to 2015, and 2016 to 2019. And we have 5 continents essentially. So this is America, this is Europe, this is Africa, this is Asia, and this is Oceania. And so if you look at these overall plots, what they're showing is the change in excess deaths due to non-optimal temperatures on the cold side, on the hot side, and then the net change. So if the black is below 0, then that means that you've seen a decrease in deaths because the decrease in cold is larger than the increase in heat here. And so in 4 out of 5 continents, you have this black square below 0 showing warming causes decrease overall deaths. And the exception here is Europe, where in the last period, you do see increase in hot temperatures overwhelming the decrease in cold temperatures. And so this study put it this way. So from the first period to the last period of the study, the global cold-related excess death ratio changed by negative 0.51 percentage points. So that's a decrease in cold deaths. And the global heat-related excess death ratio increased by 0.21 percentage points. That's an increase in heat deaths. But the decrease in cold deaths is larger than the increase in heat deaths, leading to a net reduction in the overall ratio, or a decrease in deaths from non-optimal temperatures overall. And something interesting they do in this study is extrapolate in space. And so they have maps of change in deaths from non-optimal temperatures over this time period of the study. And so greens indicate decreases in deaths and reds indicate increases in deaths. And you see more greens than reds overall. And so you can see this overall change broken down into cold and heat related. And you can see that, where there's decreases, where these, green areas are, right? This very much matches this pattern, is where the cold deaths are decreasing. This looks very similar. And this can dominate again because the cold deaths are so much more prevalent than the hot deaths. And so like you can see that in this temperature scale being much larger on the cold death side than on the heat death side. And so this net decrease in deaths with warming is something that was confirmed for the United States and Europe in this paper called Are We Adapting to Climate Change?, where they are showing these same temperature death risk relationships broken down by a decade. But what they note is, we have the same situation where most of the temperature distribution is on the left side of the minimum mortality temperature. And so warming is associated with decreases in deaths because you're getting a larger decrease in cold deaths and you're getting an increase in heat deaths, even though these functions are relatively J-shaped. And so that's what this is showing over here from this paper, that these are the different decades, and these are the sensitivities of death rates to temperature. And the fact that these are all negative means that warming causes a reduction in deaths. So here's how they say it in the paper. We find the total sensitivity of mortality to warming, the estimated effect of 1 degree Celsius temperature increase, is negative. The sensitivity being negative means reduction in deaths in all periods, a result of population in our historical sample being substantially more frequently exposed to cold than extreme heat. And then they say our findings are consistent with the broader finding that near-term warming will reduce rather than increase overall temperature-related mortality in the US. But they note that trend might reverse in the future. Okay, so historically, deaths have been decreasing due to warming because reductions in cold deaths have outweighed increases in heat deaths. And even isolating for heat deaths alone, we've seen a reduction in heat deaths due to other societal factors overwhelming the increase in temperature in terms of its effect on deaths. But what about going forward, projecting future changes in cold and heat deaths? So one thing to think about at the outset here is the rate of warming going forward. And it's important to note that the rate of warming from the 1970s to about the present is expected to be very similar to the rate of warming under a middle of the road to somewhat pessimistic, frankly, emission scenario of RCP 4.5. Where emissions in RCP 4.5 don't peak until the 2040s to 2050s, and they're nowhere near zero even by 2100. But it's a reasonable baseline to basically expect the warming rate to be similar to what we've seen historically, if not slightly better if climate goals are actually met. So we don't expect the warming rate to change necessarily, so that wouldn't necessarily be a reason to expect the historical relationships that we've seen to shift dramatically. But what tends to happen in these studies that project future changes in hot and cold deaths is what I showed before, where you basically take your derived temperature death risk relationship here, and you shift the temperature distribution under it, and then you calculate the change in deaths here. And you just basically say that it's part of your assumptions that you're not going to allow this temperature death risk relationship to change, even though we see it change a ton across space today and even across time in given locations. So here's how this gets said in papers. It'll say something like, our projections of current estimates of temperature mortality associations under future warming scenarios allow isolation of the effect of the changing climate, so just this part, but ignore contributions from other factors, including demographic changes and adaptation, which would be represented by the function changing shape. The reported figures should therefore be interpreted as potential impacts under well-defined but hypothetical scenarios and not as a prediction of future excess mortality. So even though caveats like that are often in the papers, that's not actually what happens when you have kind of the press release and then the coverage of the papers. So I think that's important to note, that this is a highly idealized projection that doesn't account for other things changing other than the temperature. So here's just another example of this highly idealized projection where we have total mortality over the 21st century. This is under 3 different emission scenarios. So this is like a close to a Paris compliant emission scenario. And this is the extremely high RCP 8.5 emission scenario. And so first, just let's look at total mortality. So basically stays flat under the Paris compliant emission scenario. Under this more middle emission scenario, you kind of have a dip mid-century, and then it goes up a little bit by the end of the century. And under the extremely high emission scenario, you have a dip and then an increase by the end of the century. And then you can see why that is broken down into the 4 different temperature categories of extreme cold, moderate heat, extreme heat. That, just like we talked about before, the moderate cold is the largest contributor to the total deaths. And in this case, it stays flat. In the higher emission scenario of RCP 6.0, this moderate cold goes down a little bit more. And in the even very, very high emission scenario, this moderate cold goes down much more. But you can see what's driving up the total deaths in the RCP 8.5 scenario is this extreme heat component. Goes from very little to very high. And so it's just kind of how much does that overwhelm the reduction in cold. And in this extreme warming scenario, you see that it does end up overwhelming the reduction from extreme cold. But again, this is without any type of adaptation changes. So some studies do try to incorporate adaptation and future wealth changes into their projections. So this is a study, Carlton et al. From 2022 that tried to do that. They try to model adaptation based on the climatological temperature of the current climate, which basically shows that a colder climate has a higher excess death ratio for, say, 35 degrees Celsius temperature than a hotter climate. So this is going to be lower on this y-axis here. So they're measuring adaptation by looking at differences across space today. And then they also look at low income compared to high income. So a lower income at the same temperature is going to have a larger death rate than a higher income country. So they can incorporate that into their equations and into their projections. But the results kind of show that the results are extremely sensitive to your projection of future income growth and how you treat adaptation, whether you allow for slow adaptation or very fast adaptation. And so that's kind of shown here with this full mortality risk of climate change in black, that this is their standard model where they get an increase in deaths by 2100. This is under the very high RCP 8.5 emission scenario. If they allow for slow adaptation, then that becomes much larger. But if they allow for fast adaptation, then even under the very high RCP 8.5 emission scenario, they're basically showing just a very small increase in deaths by the end of the century. So how fast adaptation occurs makes a very big difference. Okay, so here is a summary slide of 15 different studies looking at changes in deaths historically versus in the future. So we have historical observations on the left side, and we have projections into the future on the right side. This is going back to pre-1950 and then out to 2150. And then on the y-axis, we have increasing deaths above this dotted line and decreasing deaths below this dotted line. And I'm making a distinction between studies that look at just heat alone or just cold alone, or in black is net deaths or heat plus cold deaths. And so I think the main thing to point out here is that when you look historically, most of the studies are below this line. They're below this dotted line, meaning that we're seeing decreases in deaths historically. And it's not just the net deaths that are decreasing because cold deaths are decreasing more than heat deaths are increasing. It's even the studies that just look at heat tend to show decreases in deaths historically. And that's in contrast to the projections, which are much more on the increasing side of things, especially the ones that just look at heat. But again, I already mentioned that under this RCP 4.5 emissions scenario, we don't actually expect the temperature rate of change to change relative to the recent past. So really what's happening here with the increases in deaths in the future is just that you're assuming a halt of all the historical adaptation that we've seen. So all the things that have been changing, like the adoption of air conditioning, are implicitly assumed to just not be changing anymore in the future in order to get these large increases in the future. And so I think that's a pretty tenuous assumption. And so these projections, I think it's safe to say, should be taken with a grain of salt. Okay, so a summary here is that We see that societies are highly acclimated to local climatological temperature, so the most frequently experienced temperature or the mode of the daily temperature distribution, though we do see decreases in sensitivity to extreme temperatures over time, and that income, expressed as GDP, gross domestic product, is associated, so higher income is associated with decreased sensitivity. We've seen historically that deaths associated with non-optimal temperatures, both hot and cold, have been decreasing over time as it has gotten warmer. This is partly due to the reduction in cold deaths due to warming itself. Having less cold means less cold deaths, but it's partly due to reduced sensitivities to all non-optimal temperatures, those death risk temperature relationships flattening over time. So even isolating for heat deaths, in most locations, deaths have been decreasing over time despite warming, because those societal factors are overwhelming the influence of warming. And why is that? Well, adoption of air conditioning and well-insulated structures in homes appear to be a major factor. But other factors are important as well. So like economic factors like higher income countries have a much larger proportion of the population that works inside as opposed to, say, working in agriculture, things like that. And then other kind of more mysterious cultural behavioral factors seem to be important as well. And I think that would be a really interesting area for future research. So despite these historical trends, we see that projections into the future tend to indicate increases in deaths over the remainder of the century. But as I said, those come with the assumptions of a halt in the historical progress that society has made insulating us from non-optimal temperatures, which I think is a precarious assumption. But making sure we facilitate continued success in this region will be critical for optimizing human well-being in a changing climate.